Excellent, excellent. All right, if I switch over here to this, hey, it looks good. All right. You can't really see my graph paper on the Meet anymore. Does that mean that you guys can't see the graph paper on Zoom either?
No.
Is there too much lag here?
No. That was just that one. Oh, never mind. It's lag.
Oh, this might not work as.
Okay.
1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi.
Oh God.
No boy.
You gotta give it a second to relax.
I guess we're just gonna have to have a fun day, huh?
Oh, it's so right. Oh no.
Is it gonna get any better? 1 Mississippi, 2 Mississippi, 3 Mississippi. That's 3 Mississippi. That's better. Let's test again. 1 Mississippi, 2 Mississippi, 3. I'm gonna try it. All right, here we go.
Have you guys remembered to hydrate today?
No. I have. I'm doing a great job, although I haven't had any water in the last half an hour. So, all right, we are on lesson 3-12. We're getting near the end of this unit because I think 3-14 is the last lesson of the entire unit. So we've got like 3 more lessons left. We're out of here. All right. This is graphing logarithmic functions.
So what happens afterwards? That's what us.
Then we take a practice test. Then we take the actual test and move on to the next unit. There's like 10 units here, and I have to pick and choose which ones I want to teach.
Then we get the big boy gigantic final.
Yeah, that final's gonna be long. Oh, it's gonna be difficult. Oh, come on, make it a straight line, please. Good. Oh, there's like no lag now. That's pretty cool. Today's date is the 17th of March, 2023. That's not 23. It's St. Patrick's Day, as we have already been celebrating. All right, so I want to talk about the relationship. We'll say relation between BTWN is how you abbreviate between.
There's more lag.
Oh no, it is. It wasn't before.
Yeah. Between exponentials and logarithms. And I'm going to really abbreviate things. Ooh, it's really bad now. Now it's like 10 seconds. Why is it all over the place? That's so weird. Anywho, let's see how much you guys remember from graphing exponentials. So my first problem is going to be this. On your graph paper, I want you to graph. Like you guys don't need to technically take notes, but if you want, Diego, you see those little sticky notes over there? Sticky notes where? Grab a pile of sticky notes on the whiteboard, and then you can just put on the graph.
Sticky notes. Just pile of this one.
Just take 8, stack it.
Oh.
And then when you're done for the day, you'll put it back over there. Right?
Oh, that's cool.
That's interesting.
Yeah.
Right?
You are very smart stuff. Very smart.
All right. Let's see if I still have. That's not good. Dude, I thought they had some graphs. Hey, look, there's a graph here.
That's a bunch of pictures of some sophomores, huh?
Yeah, those are like really old pictures. I want to graph fx is equal to, let's make it as simple as possible. 2 to the power of x. That is an exponential function. I can't think of an easier exponential function. All right, so I think it is going to be super duper helpful for us to do this f of x table over here because it will make it much easier to see what's about to happen in a bit, especially when we do the inverse. All right, what happens if I plug in 0? Then I'm going to get 2 to the power of, again, I'm plugging in 0 up for the x, right?
So it'd be 2 to the power of 0 would just be 1.
Exactly. So the output is 1. If I take the input of 0, I'm trying to figure out what's the height at 0. And the height is 1. And I grab a point there. And I just plug in a bunch of x coordinates. Here we go. Let's plug in 1. That's going to be 2 to the power of 1, which is
0. Oh, it's 2.
Just 2. No. So that means if I plug in 1, what's the height? The height is going to be 2. And then, I mean, this pattern continues. You guys probably remember the graphical pattern up here. You keep multiplying that by that base.
And that dot stuck on the straight line.
Yeah, and then, yeah, so it'll look something that looks like that, but for example, I have a height of 2, I'm gonna multiply 2 by 2, and I get 4, so I get this next height of 4, and then I multiply 4 by 2.
Oh, I remember this. So it's like 1.
8.
So it's outside 1, then 1 times 2 is 2, then 2 times 2 is 4, then 4 times 2. Oh.
Yeah, exactly, and you can see the pattern over here, you're just multiplying by 2, to get to the next one, you multiply by 2, and you're multiplying by the base of the exponential function. So it's a review all the way back to our first few lessons. 2 to the power of 2, which is 4, and then it's going to be 8, and then 16, etc. Because you're just multiplying by 2 to get to the next step.
But that's because you chose 2.
That's because this number over here
Yeah.
was a 2. If it was a 3, I'd be multiplying by 3 each time.
Gotcha.
Do you guys remember what happens over here on the left-hand side?
Oh, the opposite
Yeah, I was
happens. It
gonna
goes
say
down.
It goes down like that.
No, not like
no.
that. It'd be like, how do I explain it? I remember too. Oh, it like never touches the x-axis. It continuously goes down, down, but like it never touches.
Exactly, yeah. So I mean, you can think of this as the opposite. So if I'm looking at a height of 4 and I'm trying to move from one point and I'm going to the left, the height of 4 went to a height of 2. I divided by 2. 4 divided by 2, 2. 2 divided by 2, 1. If I want to go left again, I divide by 2, and then 1 divided by 2 is a half, and then a half, and then a half, and then a half, and eventually it looks like I'm touching the x-axis. Technically, it never really does. But I mean, graphically, it does look like it does touch the x-axis, but it definitely never.
Didn't you say it's the electric fence?
Yeah, it's called the it's horizontal. Yeah, it's the horizontal asymptote. It never touches the electric fence, the x-axis in this case. Sometimes that horizontal asymptote moves. For example, if I had added 1 to this entire graph would have shifted up, and the electric fence would have shifted up with us. But I'm not doing that.
But if it was subtracted,
And subtraction would
it
go
should go down.
down. Yeah, exactly. So that's a good little review. So now on the same graph, I'm going to do another problem. I want to, is red going to be enough of a difference? I can do green too. I found that one pretty good. What's our secondary color here? Green. All right, let's go ahead and erase
You're
you.
not gonna say it's Patrick Day.
Oh yeah, of course.
Obviously.
I want us to now graph on this same coordinate plane, f of x is equal to log base 2 of x. And to do that, I'm going to invoke a few things. The first thing is I'm going to come back and I'm going to go down below this. I'm going to give you guys a sec to catch up and hydrate myself as Chloe is reminding me to do. I'm going to go all the way back to lesson like 7-6-ish when we were just working on 3-6-ish. You're in unit 3, not 7. I got confused between alphabet for a second there. And find inverses.
Oh my god, I think that's the only one I have in this notebook now.
Nice. All right, well, oh shoot, you know what we should have done? I should have called this F and this F because the whole point of writing F is to change it. I'm going to change this to a G. My bad. G of X. So G of X. I want to find what is F inverse of X. That will help me immensely with this problem. And I'll show you why. I'm going to do it with you guys because we're low on time and I want to make sure that we understand this. So I'm going to go ahead and rewrite f of x before I do anything. F of x, once again, is 2 to the power of x. Easy peasy. Okay, I'm going to switch out the f of x for a y to make my life easier. I'm going to say y is equal to 2 to the power of x. It's the same thing. It's just if I have a bunch of y's, then it's hard to distinguish between my functions. The very first step that Mr. Snell always makes a mistake on is to
Switch the x and y.
yeah, switch the x and y's. Please, Mr. Snell. It would be hilarious if I said something else and actually made the mistake. So I need to switch the x and the y's, and now I have x is equal to
Technically, on all of those videos, you made a
What?
mistake. Technically, wouldn't that be a teacher error?
yeah, and it was.
And
You logged
I
them.
didn't log any
You
of
should have
those.
logged all of them, yeah. All right, how do I get y by itself? Right now, y is the Rapunzel trapped up here In the exponent, the only way to get the Rapunzel out of the tower is to do what to both sides?
Log of 2.
Log is the only tool that gets our variable out of the exponent. So I'm going to take the log of that side. I'm going to take the log of that side. I'm going to rewrite them in here. On that side, I had x. On this side, I had a 2 to the power of y. What base should we choose? What base should we choose such that this makes it as easy as possible? You said 2. Why did you go?
Because so theoretically, if you use 2 right down there at the base, the log of 2 cancels out that 2 and cancel out the other 2, and it's just 1.
Yep, I agree. We should probably choose 2. And in general, you always choose a base that is that base, right? So I'm going to come down here and do what Diego told me to do. Cross, 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 and I get y is equal to log base 2 of x, which is interesting because do you know what that is?
G.
That's g. Look up here. Remember up here where I said, and let's go ahead and just randomly grab g of x, which is log base 2 of x. Log base 2 of x is the inverse of 2 to the power of x. Graphically, the inverse means what? Do you guys remember? This is a while back. This is like, we're going back to like September, like from last the calendar year.
November.
Graphically, what does the inverse mean? It's some sort of reflection. You guys remember what line we reflect over?
Reflecting over the
Y-axis.
origin.
The y-axis?
Oh, good guess. Good
Reflecting,
guess.
reflecting over the. Don't tell me. Don't tell me. Don't spoil it.
Okay.
Oh wait, is it the
There's like an invisible.
there's a name for it. Can I go back and find notes?
Oh,
You
yeah.
guys think of it, go for it.
Is it like? Oh my god! It's the.
What is it called?
Yeah, I don't remember it anymore.
What unit was this?
Yeah, I don't remember, to be honest. It was a really long time
You
ago.
said it was in September.
But the answer is this black line that I've just drawn right here. If I reflect over this black line, which is also known as the boundary point where y and x are the same thing, y equals x. Y equals x means you are allowed to interchange y and x, which is the algebraic way that we take an inverse, right? That was our very first step down here. We said, switch your x and your y. Because you're allowed to, because x and y are the same thing now. They are the same thing on this boundary point. Once we switch them, this point reflects, this point reflects, this point reflects. They all reflect over this line, and you have now found an inverse.
But what's the
What's the one word that you said is actually really hard to pronounce that was in this unit that I think had to do with this?
I'm thinking like asymptote is kind of a hard word.
Asymptote, yes.
Yeah, so
That's what I was gonna say is what you reflect over, but
good guess, good guess. Yeah, this y equals 0 in this case is the horizontal asymptote. Random p there for no reason because you don't even pronounce it. It's asymptote with no p. You don't pronounce it.
But where is the P?
It's in between the M and the T because English is really great at. Yeah. Anyway,
Oh, I see it.
I thought that was an O.
I thought it was an O too.
Okay.
better.
Awesome.
Yeah, don't pronounce the P. People will laugh at you in college. All right, so in here, the way that we do the algebraic inverse isn't by visually inspecting, okay, well, visually that's about the square root of 2, or sorry, the square root of 2 over 2, and therefore I go another square root of 2 over 2, and I get that point. Yes, you can do it that way, but there's a faster way. I mean, this method works. Watch. You go that distance, then that distance again, you get a point. You go that distance, oh, I don't even know. Do I go like there? I don't even know. Okay, I probably go along the diagonals, like probably like that diagonal, and I go 2.5. That's a half, and then 1, 2. This method does work, but it can lead to mistakes, and it's tedious, and there's a faster way. Let me show you the faster way of doing a reflection. A reflection over the line y equals x has this unique property that if I write the coordinates of each of these points, this is 3, 8, for example.
Oh, yeah.
This is 2, 4.
Oh, wait, wait.
This is 1, 2. This is 1, 0, et cetera, right? If I just change my x and my y, if I change 3, 8 into 8, 3, that's the reflection. And check it out. That is the answer, and that has the coordinate 8, 3. We just switched my x and my y coordinate, and I got 8, 3. That's the faster way of doing it. Just switch your x and your y coordinate. If this was 2, 4, this one must be 4,
4, 2.
Yeah, exactly. And you can check visually and be like, oh yeah, we did go to 4, and then we did go to 2. That did work out. You just keep doing that throughout the whole process. You do 2, 1, and you do
0,
this number down here is going to be 1, 0 instead of 0,
oh, wait,
1.
that's a 1. Really?
Oh wait,
It's 0, 1.
Mr. Sandell. Okay, where's the mistake? There's a mistake on there. Extra credit. Fine.
It's not. You didn't even switch it. First of all.
Yeah.
What is it? You have to be very specific in the mistake.
Well, you're supposed to switch the x and y, and you left it there. And second of all,
I was
That's-
gonna say it's supposed to be 0, 1.
oh no.
Yeah,
Oh.
that 1 point is 0, 1 because it's XY.
I'll give you guys 10 seconds. Make sure that it makes sense to you in your head silently. And if you actually got it correct, you can log the extra credit. You now have 5 more seconds.
Okay, you took a lot of my seconds. So, what I think it is that, well, I mean, it's on the x-axis, that one's on the y-axis. Well, like first, it should be 0, 1. That's the thing. But that's not the full thing. It
Okay,
should be 0, 1.
I'm going to go through and just tell you because
Ah.
that's the answer. That's the answer. This is correct. In
What?
order to log extra credit, this is incorrect.
Oh,
Ah,
it's
that's
the opposite. No,
0,
it's 0,
the other
1.
This one should have been 0,
0.
That's the mistake.
Dang it.
So if you caught that,
No, I didn't catch that.
I want extra credit.
then you can get the extra credit. I should have. I don't know. That was me being silly. I haven't made that mistake in a really, really long time.
That is a silly mistake.
Anyway, yeah, you just switch your x and y coordinates. So, how do we do this problem fast? Let's go ahead and give us another graph. Let's see how fast we can go through an easy problem. So, was that, that's kind of like the lesson part. Let's do an example. Full speed example. Full send example.
Full set.
Okay. Yes, queen.
Example number 1. Grab another sticky note for your graph, Diego.
I think I'm just gonna watch you.
Okay, that's
So
fine.
I was getting lost myself.
Is this the graph paper? Why do I have that in my notes?
It's important for something.
Probably, maybe. I don't know. All right, example number 1. Let me actually, move you down so I can write my problem. My problem is this. I want you to graph h of x is equal to log base 3 of x. Here's how I would start out this problem. The fastest way that I can think of doing it is Chloe's table map. I would say, okay, well, I'm going to do x, and then I'm going to do h inverse of x, aka 3 to the power of x. Because I know how to do that. The inverse of log base 3 is 3 to the power of x. You just put the 3 and then
Oh,
X, right?
oh yeah.
these are inverses of each other. We've proven that like up here that's how it works. And then once I get this table made up, I'm going to take the inverse and just switch these two and be done. I'll show you what
So
I
it'd
mean.
be
The
h
negative
equals
1 and
x.
x. Negative 1, yeah. Or would it be negative 1 equals
I don't need very many points. Oh.
h of x?
Okay, so for example, if I plug in 0, this will be 3 to the power of 0, which is going to be equal to 1. If I do 1, this is going to be 3 to the power of 1, which is going to be equal to 3. And I don't even need a pattern because I know to get from u to u, I'm just multiplying by 3, which came from that 3, right? Yes. Okay, so let's go fast. Ready, set. It goes 2, comma.
2, comma 9.
Good. Oh, I want to do blue. And it's going to go 3, comma
27.
Oh, 27.
27. And I can't really go any
Is
farther.
the next one 81? Or wait, really?
Yeah, and the next one would be 81,
Let's
but
go.
we're already off the graph, so it's kind of silly to keep going, but it's good to know, right? All right, so
Well, it's because like it's 3 times 3 times 3
So
times
20.
3.
Oh, okay.
I know, I just memorized that for some reason. I don't know what it is after that.
Oh, yeah. 9 times 9 is 21.
yeah, that's how I do. Anyway, so here's how I'm going to do this problem now. Now I'm going to do underneath this. You don't even need to write this table in. I'm just doing it so that's in our notes for forever. I'm going to do x comma h of x, aka the thing that I'm actually trying to do over here. And here we go. I'm going to go ahead and make my table. And I'm going to switch. This 1 is going to come over here, and this 0 is going to come over here. They're going to switch, right? That's the definition of an inverse. You switch the x and the y's.
Oh yeah, switch 1 over 0.
1 comma 0.
3 comma 1.
Oh, 3 comma.
Comma 1.
9 comma 2.
3. Again, these are the counting up numbers over here, just like these were the counting up numbers over here, right?
Oh, so
Yeah.
technically there's only going to be 3 numbers on that graph.
Wait, but that's confusing because it looks like you wrote x and x twice.
No, that's different.
And
Now
I'm-
it's x. Now it's h of x.
H of x is
H inverse versus
Y.
H. Yeah, so, and you probably are seeing there's an even more shortcutting method, which is just start by putting your x values over here and then do your pattern over here and multiply by 3. That also is even faster than my method. But again, this is the general method that you can improve upon. Here we go. Let's graph this. 1 comma 0. 1 comma 0. I actually did correct this. Whew. All right. And then I'm going to do 3 comma 1. So I go 3 comma 1. And then I'm going to go 9 comma 2. So I'm going to go 9 comma 2. I don't see what's really happening. We never even finished this one up here, did we?
I have no clue.
We should really finish this one so we can see what's happening, because we know what's happening up here. Up here, this blue line is being connected to all of these points. But what's going to happen in this general area? I have a horizontal asymptote. When I reflect this line, for example, let's go ahead and pretend for a second that -8 comma 0 is a point. It's not. You never get 0. This is a falsehood. I'm going to go ahead and lie. I'm going to go ahead and in big letters, that's a lie. But it's a lie that's helpful. Because if I graph the inverse of this, the inverse is going to be 0 comma -8. I switch them. 0 comma -8 is going to live right there. So I'm going to go ahead and put that point on my graph, which means somehow I'm going to get from this point to this point. It's going to look like that curve, which means I have to be doing this.
Yeah, but I was gonna say, doesn't it just almost touch it doesn't touch the x-axis or the.
It never touches the
Yeah.
y-axis, just
The
like
Y.
we never used to touch the x-axis. But on the graph, it basically looks like you're on top of it. You get so close you can't distinguish between your line and the y-axis.
Yeah.
So that's our final answer. And here's the thing. You will 100% of the time, all logarithms, no matter the base, will always have this vertical and that hard word asymptote.
So you want us to.
And it will usually be right here unless I shift it left or right.
But do we need to graph both sides?
There's no both sides. This is the entire graph done.
Okay, that's the other part is just what it's given.
Yeah, this was to learn the relationship between how to get from here to here. We don't need that anymore. That's useless to us unless we need to rederive the entire process. Just do this over and over again. So down here, I know that this is going to go down like that. It's going to be on that vertical asymptote. So I'm going to go ahead and just draw my line. Say that's going to come down through there, and it's going to come up through here, close enough. And there's my graph done. There's my logarithm.
But we also have to label the points, right?
I mean, you have to label 3. You don't have to label the coordinates of points, but it's very clear that I have 3 points in my graph. I'm going to say, no matter what, you have to do 3 points. Let me give you another one. We still have 6 minutes left of class. I need to add another piece of paper. Is there a way to add another piece of paper without doing it this long way where you go like this, drag this up, put it there, drag it there? It's got to be a faster way. Anyway, let's go ahead and do example number 2. Is that what we're at?
I thought you used to be able to just add a new paper.
Yeah, but I have pages behind this already. So if I drag it, it just goes to the next page.
Yeah.
Example 2. Zoom kids, am I going too fast?
No, you're good.
Okay, cool. Slightly harder one. Graph 1/2. Sorry, where's my f of x? Letter.
P.
P of X is equal to log base 1/2 of X plus 1.
Ew.
Yeah, we have to slowly increase the dial difficulty. From here, I have to take the inverse of that function. I don't know what that looks like. I'm not sure what's going to happen there, so I have to do it the long way. I have to actually do the inverse function. So let's go ahead and find, we're going to find P inverse of X. And that'll help us out because I know how to graph that one. So I'm going to go ahead and say y is equal to log base 1/2 of X plus 1. Switch my X and my Y. So this is now X is equal to log base 1/2 of X plus Y plus 1.
Or Y plus
And then I'm going to try to get this Y by itself. So how do I get that Y by itself? Well, the only way to get rid of a logarithm is exponentiation with what base?
1 1/2. 1/2.
1/2 the power of all that. And I should do this in 2 separate lines because we're doing the notes. I want to be nice and neat and tidy. 1/2 and 1/2 are new bases. Our old powers are X, and our old powers were log base 1/2 of Y plus 1. And what should theoretically happen? Cancel, cancel, cancel. And I'm left with 1/2 is equal to Y, sorry, 1/2 power of X. Where'd that go? Y
Teacher error.
plus 1. I counted before you did. But yeah.
So then you do it.
And then from there, then I subtract 1, right?
Yeah, that's what I'm
Minus 1, minus 1, and I finally get Y is equal to 1/2 of X to the power of X, and then minus 1. All right, so I'm going to make a table for you. So let's make a table. Ready, set. And this is going to be a table of X and P inverse of X, because that's what we just found. P inverse of X is this thing up here. You don't need too many points. Let's go ahead and just do 0. If I plug in 0, I'm going to have 1/2 to the power of 0 minus 1,
So that's
which is anything to the power of 0 is
0. Or 1, I mean.
anything to the power of 0 is 1. And I'll have 1 minus 1.
Oh, that makes sense.
Let's try plugging in a 1. I'm going to have 1/2 to the power of 1. Okay, what is someone other than Emma? What's 1/2 to the power of 1?
So kids. Or
Exactly.
Yeah,
1/2. Then- exactly. And then what is that 1/2 minus 1?
Negative 1/2.
Is equal to negative 1/2.
Oh my god. Big brain.
Good. And you can kind of tell that if I go down this way, it's probably going to be getting fraction here. More and more fraction near, like smaller as a fraction. So I want to go the other way. Here. Sorry for people taking paper notes. You're just going to have to keep writing it down here, and you're not going to see the clear pattern. I have technology, so I'm going to go ahead and shift all of you. Come on.
we should make Mr. Sedell a definition or a
Yeah.
dictionary so that he can have fractionary. Wait, what was that? More fraction?
More fraction.
More fraction.
Perfect. Yep. Well, though, it appears to be about that time.
Oh yeah, it's on point.
Well, what I was about to do is go -1 and -2 and -3. That's why I'm extending the table. We'll pick up on Monday.
Thank you for the pie, Mr. Sedell.
Yeah, you're welcome.
Was that the bell?
That is indeed the bell. It is now 6 period. 6th period goes from 11:33 to 12:10. Then we have lunch, and 7th period starts at 12:43.
Bye, George.
Got it. Bye. Bye.
My question is really mad.